What I'd like to show here is a cold fusion experiment that we're running at the Naval Weapons Center in China Lake, California. We are running two cells simultaneously in the water bath here, cell A and cell B. We're running exactly the same current through both cells. The current is provided by this instrument. The amount of current we're passing through is, at present, it is 525 milliamps. We are reading the cell voltage. The cell voltage for cell A is displayed on this meter. The voltage for cell B is displayed on this meter. At the same time, we are recording the cell potentials on the strip chart recorder. The green line shows the voltage of cell A. The red line shows the voltage of cell B. There is always an increase in voltage when you add the D2O, and then the voltage gradually goes down as the electrolysis proceeds. What we have right here is a probe to measure any radiation. This is mostly for safety. We have never seen any radiation to be concerned about. We're running this in a constant temperature bath. This gives us the temperature of the bath, which is 27.50 degrees centigrade. And we are reading the temperature inside the cell. The palladium electrode and all electrolysis is taking place inside the cell, which you cannot see. But we have thermistors that record the temperature on the outside of the cell surface. We have two thermistors in each cell that are recording the temperature. So we have a temperature reading of inside the cell and of the cell bath, which we need for the calorimetric measurements. This shows what is actually down inside the cell. We have a short palladium rod of a diameter of 0.635 centimeters. Tightly coiled around the palladium rod is a counter electrode, platinum counter electrode. And so these two electrodes is where the electrolysis of the solution is taking place. This is filled with D2O, the inside test tube here. The two dark spots show where we measure the temperature. These are two thermistors that are attached tightly to the outside surface of the electrochemical cell. Temperature readings are displayed here. This is for measuring the temperature inside the cell. We have two thermistors inside each cell, and we can read the temperature to 1/100th of a degree. For example, right now on thermistor 1, we're reading a temperature of 39.99 degrees Celsius in cell A. If I press this button, we're reading 39.52 degrees Celsius from the thermistor in cell B. This is a scalar rate meter that is counting the radiation, and what you see on the screen is mostly just the radiation from the background cosmic rays or whatever. But we print this out every 12 hours to have a record of the radiation. We keep track of the data in the notebook. Once every hour or 2 hours, we record the current, the temperature of the bath, the room temperature, and the temperature from the four thermistors inside the two cells. From this, we can calculate the amount of heat that is going into our system and the amount of heat that is flowing out. This gives us our calorimetric data to determine when we have an excess heat event taking place. At the same time, the electrodes are down inside the cell, which you cannot see. We have electrolysis going on, which is generating deuterium and oxygen gases. These gases come up through the cell and into these lines. These lines were well flushed with nitrogen before we ever connected them to the cells, but the gas flows through the lines and into a 500 milliliter flask back here, and then come out of the flask and through an oil bubbler. You can see gas bubbles coming out. That is deuterium gas and oxygen gas as a result of the electrolysis. Anytime that we see excess heat, we can close the flask off and then do analysis for helium as a product. And that is the main feature of what we've done recently, is that we have seen helium, a product present in the gases coming off these cells.
The gas system is flushed out, and then the effluent gas is run many flasks full through the collection flask, and then the effluent gas flows out the bubbler. You can see here the bubbler maintains a positive pressure on the gas system, so any leakage would be from the inside to the outside, therefore to prevent contamination by the air. The effluent gas that's collected in a flask like this is then shipped to the University of Texas at Austin, where it's analyzed by mass spectrometry. Yeah, I was at the University of Texas at the time the analyses were done. I did the analysis of the effluent gas, analyzing for helium-3 and helium-4. The effluent gas sample is pulled into activated charcoal cryofilter, which acts as a pump, and then the gas from there is filtered through a second stage into the mass spectrometer, which analyzes for helium-3 and helium-4. The mass spectrometer was capable of resolving helium-4 versus deuterium, both which have a nominal mass of 4. It could tell the difference between helium and deuterium. The bypasses on the filter were used to allow connection of the flask without contaminating the lines with air, which would contaminate it with helium. This is a single-stage activated charcoal cryofilter, similar but not the same as the one we used at the University of Texas to filter out all gases except helium. The activated charcoal is in this section of the filter, and this is the bypass which allowed the lines to be cleared out of any residual air before the effluent gas flask was hooked up. But this is only one stage, a one-stage filter, whereas we used a two-stage filter at the University of Texas. This section here was in a liquid nitrogen dewar, or would be when we used it. The lines leading to the mass spectrometer are cleared of all air through this bypass, and then the activated charcoal cryofilter, the activated charcoal part of the cryofilter is cooled with liquid nitrogen. This part is cooled with liquid nitrogen, and the effluent gas would be then run through the cold activated charcoal. The activated charcoal will absorb any gas except helium.